Welcome to the fourth video of Chapter 3. In this video, we're going to be studying the ideal gas equation of state. So what we just went over in the prior section was looking at properties of phase change substances. Namely, in this course, that mostly entails refrigerant, R134A, or water. Ideal gas is typically a gas that does not change state during the thermodynamic processes that we will be analyzing in this class. So an equation of state is basically any equation that relates the pressure, temperature, and specific volume of a substance. So we get that the pressure is a function of temperature and specific volume, or specific volume is a function of temperature and pressure. More generally, property relations that involve other properties of a substance at equilibrium states. So you can also get, for example, internal energy and enthalpy as a function of other properties. What we're going to be mainly dealing with is an ideal gas. An ideal gas is a model substance of infinitesimally small particles that do not interact. And the equation of state for an ideal gas, which I imagine you have probably seen in high school in some form, is pressure times volume equals mass times the gas constant times T. There's other ways to write it. There's pressure times volume times number of moles times the universal gas constant times T. Also pressure times specific volume, that's if you divide this through by mass, volume divided by mass becomes specific volume, equals RT, or pressure times specific volume on a molar basis equals universal gas constant times T. So again, R bar is the universal gas constant. It is on a molar basis, and it is the same value for every single gas. And R is a gas constant, and it is different for different gases. It's a different value for each gas. And there's a relationship to calculate the gas constant as a function of the universal gas constant. It's basically the universal gas constant divided by molarity. We will be using the ideal gas law in this class significantly. Again, here are all the variables. R is the gas constant. P is pressure, but absolute pressure. T is temperature, not only temperature, but absolute temperature. And nu is specific volume. And again, R is different for each gas. The value is different for each gas. And the universal gas constant, or R bar, is the same for all gases. Right? So the gas constant, R takes on a different value for each gas, and R can be expressed in terms of the universal gas constant, as we looked at earlier. Basically is the universal gas constant divided by molarity. Again, R and RU and R bar are the same thing, where M is molecular mass or molecular weight. So as an example, here's a small table that lists air, helium, argon, and nitrogen, and it gives you a different gas constant for each one. Again, this is the gas constant, not the universal gas constant. Let's just look real quick and try to discern the difference between mass versus moles, right? Specific properties, right? When I talk the word specific, specific means per mass, but specific properties can be defined on a per mass or a per mole basis. So if you look at something called a molar fraction of a compound would be the number of moles of that compound divided by the molarity, right? Or I'm sorry, the mass fraction would be the total mass. The fraction would be the total number of the mass divided by the total mass, or that you would have the molar fraction, which would be the number of moles of one substance divided by the total number of moles. Again, where N is the mole number and M is molarity. Mass is equal to the number of moles times molarity. The ideal gas equation of state can also be written on a molar basis, right? Pressure times volume equals number of moles times R bar T, where, or pressure times specific volume on a molar basis, if I divide through by N, right? I get N over here and cancels out, where I get my specific volume on a molar basis equals R bar T. So again, this would be the mass fraction, where this would be total mass. I should probably make sure that I designate the difference between, that looks like molarity. So I get the total mass of something divided by the mass of one object divided by the total mass, or the total number of moles divided by the number of moles of a system, which is molar fraction. So next thing we'll look at is property ratio. So by writing the ideal gas equation of state for twice for a fixed mass and simplifying, the properties of an ideal gas at two state points can be related as follows, right? So let's look. If I write out my ideal gas law, PV equals MRT, what I can do is equate the change in properties between two states. So I have an ideal gas undergoing a process from state 1 to state 2. If I can take my equation, for example, for a constant mass process, right, I can, for example, pull on the right-hand side of the equation everything that's constant, and the left-hand side equation everything that's changing, right? So if I change from state 1 to state 2, the pressure, volume, and temperature change, but I have constant volume. This tells me that P1 times V1 over T1 for state 1 equals P2 V2 over T2 for state 2. And I can do this for different processes, right? What if I have an isothermal process, right? An isothermal closed system. So I have an isothermal process going through a closed system going through an isothermal process. So I have constant temperature and constant mass. So PV equals MRT. I end up getting, on the left-hand side of the equation, everything is changing. So P1 V1 equals MRT. If MRT is constant, right, mass and temperature are constant during the process, that means I get P1 V1 equals P2 V2, which would be the relationship between pressure and volume of state 1 and state 2 for an ideal gas undergoing an isothermal process. Right, so that is what the ideal gas equation is very good for, is being able to relate pressure, volume, and temperature together. The ideal gas equation is mostly useful for low densities, low pressures, and high temperatures. Right, so let's look at a phase diagram real quick. Right, so here's temperature on the y-axis, here's volume on the x-axis. Here is the saturation curve. If I look in a superheated gas region, which is this area, right, I can go so far into the super gas region that I end up going into the ideal gas region, right? If you think about it, you're breathing air. Air is mostly nitrogen and oxygen and other gases like carbon dioxide, argon, etc. We're breathing in the gases that constitute air. We're breathing in that gas at a superheated state, right? Nitrogen condenses at a super low temperature, as well as oxygen. So right now, we're breathing it in as a superheated vapor, but it's so much a superheated vapor that it's actually in this ideal gas region. I hope that makes sense. All right, let's look at compressibility. What is a compressibility factor? The behavior of real gases can deviate at times from that of an ideal gas. This deviation can accurately be accounted for by the introduction of a correlation factor called the compressibility factor. So let's look. Here's the ideal gas law, right, written in specific terms. P nu equals RT. The compressibility factor introduces a factor into the ideal gas law. And the closer is this Z is to 1, the closer to an ideal gas it is. But what happens is when you deviate from the ideal gas, you can actually compute a value for Z that corrects for the deviation from an ideal gas. How do we use, or how do we quantify that value of Z? Well, we have to compute something called the reduced temperature and a reduced pressure. It's pretty simple to compute. You take the temperature that the gas is at and you divide it by a property that's tabulated called the critical temperature. And the reduced pressure is a non-dimensional number as well, where you take the pressure of the ideal gas and you divide it by something called the critical pressure. And you figure out what the reduced temperature and reduced pressure is. And you go to something called the compressibility chart. The generalized compressibility chart is a general chart for obtaining a compressibility factor for real gases based on those reduced properties. And here it is. This is the compressibility chart. So let's look at how to use it. We have here on the y-axis the compressibility factor Z, which you're trying to determine. You have on here the x-axis, the reduced pressure. So let's say I give you an ideal gas, or a gas that's at a temperature and a pressure. You look up the critical temperature and the critical pressure, and you compute the reduced temperature and the reduced pressure. For a fixed reduced pressure, you follow that line until you intersect one of these purple lines. Each line represents a different reduced temperature, 2, 1.5, 1.3, all the way down to 1. So you find out where you intersect that point. Let's say you have a reduced temperature that you calculate as 1.5, right? You follow the reduced pressure line until you hit the reduced temperature, and then you find the corresponding compressibility factor. Now, if you lie anywhere, for example, between 1.5 and 2, you just sort of have to try your best to interpolate. Right, best thing to do is to go ahead and try an example problem. So the next slide, we have just that. This is actually a problem from an exam that I gave a number of years ago. The problem reads, determine the volume in meters cubed occupied by 40 kilograms of nitrogen at 17 megapascals and 180 degrees Kelvin, or 180 Kelvin, not 180 degrees Kelvin, right? So, simple schematic, just nitrogen in a tank where we have 40 kilograms, temperature of 180 Kelvin, and a pressure of 17 megapascals. Right? So what do we do with that? Well, the first step is to find the critical properties. So if you go back of your book to table, I believe it's A1. So if you go to table A1 for nitrogen, you can find that your critical temperature is 126.2 Kelvin and your critical pressure is 3.39 megapascals. From there, you find your reduced temperature and your reduced pressure. So whatever your temperature is, which is 180 Kelvin, divided by the critical, you divide that through, you get 1.43. The pressure, which is 17 megapascals, and the critical pressure, which is 3.39, you get about 5. So let's go back to the table. We have reduced pressure of 5. And we have a critical pressure temperature of about 1.43, which lands us about right there. Right, so let's say right about there. That gives us a critical or a compressibility of about 0.8. So that chart can be found as figure A15. So if you do that, you find that your compressibility is about 0.8. And then you do your corrected ideal gas law, PV equals Z mRT. Right, I'll go to the next slide. Solve for Z. I'm sorry, not for Z. I'll solve for volume. That's what we're trying to get. So I get Z mRT divided by pressure. So I get 0.8 for the compressibility. The mass is 40 kilograms. If you go back to the chart, you'll find that the gas constant for nitrogen is 0.2968. The temperature is 180 Kelvin, and the pressure is 17,000 kilopascals. You find that the volume is 0.1 meters cubed. So that is a basic approach on how to use the compressibility factor. Right. So far, all of these deal with the ideal gas law or deviations from the ideal gas law. We will be using the ideal gas law extensively and throughout the rest of the course in many ways. So make sure you process how to use that. There are, of course, other equations of state. We will not be using many of them, but just give an idea. There's the ideal equations. There's something called van der Waals equation of state. I'm not going to write it out, but it is used from time to time. We are not going to be using it in this course. And there are several other ones as well, although at times I have covered it in this class, but since we're not going to be using it very much, I'm only going to mention them by name and not mention them for use.